Hello everybody. For this video we're going to be taking a look at a few more theorems that involve triangles and the idea of proportionality. And so to start off with, we need to define a phrase that's going to come up a few times in these theorems. It says, suppose points L and M lie on segments AB and CD respectively. So let's get an idea of what that might look like. I'll come up here and I will sketch out point A, segment AB that will have point L on it, and then we have segment. Let's do this one in blue. Segment CD that will have point M on it right here. And it says if AL over LB, so if the one part of the pink segment over the other part is equal to CM over MD, so a part of the blue segment over the other part of the blue segment, we can say that AB and CD are divided proportionally, because we can make, they have been divided into points L and M have divided segments AB and CD into two smaller segments. And when we set up a ratio of those two segments for each original segment, those two ratios are equal, so it's obviously a proportion. So we say that those two segments have been divided proportionally. And so let's see how that pops up in a few theorems, starting with Theorem 7-3, or the triangle proportionality theorem. And this theorem says that if a line that is parallel to one side of a triangle intersects the other two sides, then it divides those sides proportionally. So what we'd be looking at is a diagram like what we have over here, where we have a segment DE parallel to a segment AB. And segment DE is intersecting the two sides of triangle ABC that it's not parallel to. So it's parallel to the third side, intersecting the other two sides. So that's the situation that we are describing in the hypothesis of this theorem. And so if that happens, if segment DE is parallel to segment AB, then according to Theorem 7-3, it will divide side AC and side BC proportionally. And so what would that mean? Well, it's similar to what we have up here, where we had segment AB and segment CD divided proportionally by points L and M. Now we have points D and E dividing these two sides proportionally. So what we would know is that the ratio of CD to AD would equal the ratio of CE to EB. I'm also going to go ahead and write that proportion one other way by switching the AD and the CE. We learned a few lessons back that you can do that in a proportion. You can kind of flip-flop these terms here, what we would call the means of this proportion, and you would end up with an equivalent proportion. So I want to go ahead and write it in that way as well. It would look like CD over CE equaling AD over EB. AD over EB. And so where this is coming from is it's coming from, in a way, the idea of triangle similarity, and once we know triangles being similar, that we would know that the sides are proportional. Because if these two lines are parallel, then it would create some corresponding angles here and here, as well as here and here, that are congruent, giving us angle-angle similarity for triangle CDE and triangle CAB. And from that, we could end up stating, I'm not going to go through the whole proof, but we could end up stating that with these two segments parallel, this proportion would result. And so let's take a look at a couple ways that we might end up using the triangle proportionality theorem. Let's look at example 1 right here, where we have a triangle with a segment that is intersecting two sides of the triangle and is parallel to the third. And as we would know, that there's going to be some proportions that would result from this situation. And so I've got 6 proportions over here that I want to fill in a missing term for, just using this idea of the triangle proportionality theorem. And so the first one says A over J, so this segment right here's length over this entire segment's length, would equal C over, and we can probably see that that would be K, C over K. And this is actually, this would be two of the ratios that would come from this triangle being similar to this larger triangle right here. Again, like we stated, because we would know that this angle and this angle would be congruent, and this angle and this angle would be congruent, we would know that the corresponding sides of the smaller triangle and the bigger triangle would be proportional. And what that allows us to do, and I'm going to add a couple letters onto this diagram, I'm going to put an X here and a Y here, we would actually be able to say that in addition to these two ratios being equal to each other, a third ratio could be added to this proportion that would be X over Y, because that would be the third pair of corresponding sides between the smaller triangle and the bigger triangle. That's actually going to come up as important in a problem coming up down here in example 2. So I just wanted to throw that up there as well. The other proportions we would have, let's go ahead and fill those out. We would have A over C equals J over K. This is just taking this earlier proportion and switching the means with one another. So there's going to be a K down there as well. Letter C is comparing B to J, and that would equal D over K. A over B, this is pretty much the triangle proportionality theorem stated, that this side, the top part of this side of the larger triangle compared to the bottom part would equal C over D. So there's a D right there. And then if we switch the mean terms right here, the B and the C, we would have A over C equals B over D. And lastly, we can compare B to D, and that would equal J over K. So you'd have a K right there. So all of these different proportions would result from this situation where we have a segment intersecting two sides of a triangle and being parallel to the third side right here. Example 2, we're going to actually throw some numbers on a diagram like that, and we're going to see what the triangle proportionality theorem would allow us to conclude about some side lengths here. So to start with, we notice again we have that situation of a segment parallel to one side of a triangle and intersecting the other two sides. And we have some side lengths that we can put on here. We have the length of CE is given to us as 3, the length of EB given to us as 6, the length of DE given to us as 3.5, and we are supposed to find the length of AB. And so you can see this is that proportion that I kind of extended right up here in part A of example 2, where we put X and Y on the third side of the small triangle and the big triangle. And so what we would notice is that if we set up a proportion that would say, let's see, DE over AB, that should equal EC over, and it wouldn't be over EB. EC is the side of the smaller triangle in this picture, and it would be in a ratio with its corresponding side from the bigger triangle, which would be segment CB. So we'll put a CB right there. And so now if we fill in some lengths, we have DE at 3.5. We have AB as an unknown, so we'll put an X down there, and we'll solve for that X here in a second. EC has a length of 3, and CB is not the 6, it's a length of 3 plus 6, which would be 9. And so now if we do some cross multiplying, we should be able to solve for our X. 3.5 times 9, that's going to give us 31.5, would equal 3 times X, or 3X. So if we divide both of these sides by 3, we will get x equals 10.5. So the length of AB would be 10.5 right there. Now next, let's look at another set of values that could be applied to this diagram. CA having a length of 12. So this length, this length is 12. DA having a length of 8. CE, so I'm going to get rid of this 3 here for a second. CE has a length of 6. And the question is, what is this length going to be right there? Length of CB. And so what we notice is if we have this side right here, DA, and the whole thing, AC, we'll make a ratio out of those, and we'll realize that would be equal to the ratio of BE over BC, or CB. I'll put CB. Now, CB is what we're trying to eventually get, right? But if we can find, or CB is what we're trying to eventually get. But if we can find BE, that would help us. But as if we start filling in this, diagram right here, we would probably have to use an X for BE, and we don't know that. So AD would be an 8, AC would be a 12, BE would be an X. Now CB, since 6 is the length of CE and X is the length of EB, CB would be an X plus 6. Now we could cross multiply this and solve it, and that would be fine. But there's another way we could do this problem. Because if AD is 8 and AC is 12, we should realize that this is going to be a 4 right there. And now there's a ratio that we could set up that would say 4 over 12, or DC over AC, would equal 6 over this unknown, and since I used an X up here, I'll put a Y right there, would equal 6 over segment BC, which we're going to call Y. Now you can see this ratio is going to be, or this proportion is going to be a lot easier to solve than this one, because we'd have to do a little bit more algebra work to get the X isolated once we cross multiplied on this one. But over here, we're going to have 4 times Y equals 6 times 12, and 6 times 12 is 72. And now if we divide both sides by 4, we would get that Y is equal to 18. And so the length of CB would be 18. And so there's a couple applications of that triangle proportionality theorem that we just learned. Now let's see what else there is to take a look at for this section. There's going to be a corollary to the triangle proportionality theorem. It's going to say if 3 parallel lines intersect 2 transversals, then they divide the transversals proportionally. So a slightly different scenario. We don't have a triangle now in this scenario, but we do have 3 parallel lines intersecting 2 different transversals. And so what this would mean, and for this particular diagram, the corollary would say that if line LQ is parallel to line MP, and that is parallel to line NR, then these 2 transversals would be divided proportionally, which would say that LM over MN would equal QP over PR. Or, again, we could switch the means in this proportion, and we could make it say LM over QP, so comparing LM to QP, would equal MN over PR. MN right here over PR right there. So let's take a look at that. Let's apply it to a diagram down here where we have 3 parallel lines, 2 transversals, and we have some side lengths, or some segment lengths that we can put in this diagram. A having a value of 2, B having a value of 3, C having a value of 5, and then D being the side that we're trying to find. And so since we do have three parallel lines and two transversals, we know that there is a proportion that we can set up that would look like A over B equaling C over D. So filling in the numbers here, it would be 2 over 3 equals 5 over x. Cross multiply that, and you have 2x equals 3 times 5, or 2x equals 15. Divide the 15 by 2, and we would have x equaling, we'll say x equals 7.5. So D would have a length of 7.5. Now if we change some of these values, we could probably solve another proportion here. Let me get rid of these. Get rid of these values, and I'll change them into what they have in part B. If you wanted right now, you could go ahead and pause this video and you can try and work out part B yourself. I'm going to put a 4 here for A. I'm going to put an 8 here for B. And I'm going to put a 5 here for C. And then the question is asking, what does C plus D equal? Well, there's a number of different ways I could set this one up. I could put A over A plus B equaling C over C plus D. But what I could do here is I could just try and find D, and then I could add it to the 5 to find what the length of C plus D is. And that's the way I'm going to do it. So I'm going to set up an A over B equals C over D proportion, which is going to look like 4 over 8 equals 5 over, I'll use y since I used x up there. And now when I cross multiply that, I'll have 4y equaling 5 times 8. So 4y equals 40, and y equals 10. So D has a value of 10. The problem is asking what is C plus D, so we would just take 5 plus 10, and we would say that it's 15. So that's the corollary to the triangle proportionality theorem. There is one more theorem that we're going to take a look at in this video. It's called the triangle Angle-Bisector theorem. And it says that if a ray bisects an angle of a triangle, then it divides the opposite side into segments proportional to the other two sides of the triangle. So in this picture here, we notice that we're going to say that ray BD is bisecting angle ABC. So if ray BD bisects angle ABC, or another way we could have said it is we could have said if angle 1 is congruent to angle 2. I guess that would have been shorter. We'll leave it as this. If ray BD bisects angle ABC, then according to the triangle Angle-Bisector theorem, ray BD is going to divide this side, the side opposite the angle that's been bisected, in a way that is proportional, that the two parts of it are proportional to the two other sides of the triangle. And so what that would look like is it would look like a proportion that compares AD to AB in a ratio, and that ratio would equal CD over BC. Or, just to kind of keep this, stay consistent with what we've done with some of the other proportions in this video, we're going to switch the means here to create another proportion that would also be true, and it would say AD over CD. So we could just say this part of the third side over this part of the third side would equal this side of the triangle AB over the other side of the triangle BC. So either one of these proportions would result when ray BD is bisecting angle ABC. So if we wanted to apply that in a problem down here in example 4, we would notice that segment BD has bisected angle ABC. We got a couple of congruent angles right here and here. And so we know the triangle Angle-Bisector theorem will apply. And what it will mean in this picture is that segment AD over segment AB would have to equal segment CD over segment BC. And what we're trying to find is the length of AC here. But if I can find the length of DC, if I can put an x right there and figure out what the value of that x is, I can add it to 10 because I know that the length of AC will be the length of AD plus the length of DC. So it will be 10 plus something here, what this x is equal to. So if I can find that x, I can put that there, add it to the 10, and that would give me the length of AC. So we know this proportion will be true. If we fill in the given values for the diagram, we'll have a 10 over 12 equals CD, which is x, over BC, which is 24. Cross multiply this, we would have 10 times 24 equals 12 times x. That would be 240 equals 12x. Divide both of these sides by 12. And we get that x equals 20. So that is the length of DC. So put that down here, and we would know that the length of AC is equal to 10 plus 20, which is 30. And so that's an application of that triangle angle-bisector theorem. Now there are obviously some more complicated applications of these theorems, but this is the basics. And so it should give you everything you need to know to solve some of those more complicated problems. So good luck to you on that, and stop by and see me on the next video. Have a great one.